We're going to be going into a little bit of detail on the technology behind the measuring cell that is produced by Endress+Hauser. As Nikki did mention, everyone, we do have that bar in the middle. Pat and I do have items, devices that we will be putting towards our camera, so I do recommend that you make your video screen a little bit bigger throughout the presentation, and we'll be showing you hands-on breakdowns of all of the transmitter pieces. So without further ado, Pat Irwin.
Good afternoon, everybody. Thank you for joining. I hope everybody's safe and their families are doing well. Today, I wanted to take the opportunity to show you the pressure technology differences between what you have in the plant. Some of you have Endress+Hauser. We thank you for that. But also show you the evolution of technologies and what Endress+Hauser has done to improve the performance of the pressure transmitters. But before we get into that, I want to cover a safety moment. I think that's just best practices, especially in our new norm day and age. We'll go over the pressure sensor design technologies, calibration methods with the Endress+Hauser product, and then open it for question and answers. We wanted to keep this simple today, just around the technologies. So for a safety moment, I know where most of us are at home, and for those of you at the plant, thank you very much for your services going in and assisting and engineers and any parts that are touch points. Very quickly, you know, we're going to be working our way back into our jobs, and we're going to be getting back out into the public. So, you know, this is just a friendly reminder that we need to keep the best practices going and follow your company's policies. I know Endress+Hauser and Vector are putting together company policies as we ramp up. But again, you know, just watch your, clean services, stay home if you're sick, keeping your distance, just be aware of your health, and just to try to avoid touching your face. And I think we've all learned this very well. Wash your hands or use your sanitizers. So pressure sensor design technologies. To give you a little bit of a historical perspective, pressure technologies have been around on the electronic measurement side since about the late 1960s, about 1968. Before that, we had pneumatics. And so you were running 3 to 15 PSI signals. The devices that were measuring the differential or the gauge pressure or the absolute, they were essentially had a bellows in them, and then they provided literally a pneumatic output. So manufacturers, several of the key ones, decided in the late 60s to create an electronic device. So if you think about a DP sensor, think about a U-tube manometer. You see your HVAC guys use it when they come over to your house to check your air conditioning. And what it is, it's literally a tube that is bent in a U shape, and you fill it with a liquid. And typically, the liquid you'll see used by the HVAC contractors is red. It carries a different specific gravity of water. It's a little heavier than a specific gravity of 1. But at the end of the day, what they do is they will apply a pressure to one of those sides of that U-tube. And as pressure is applied, it will basically move, basically showing a pressure change. And if you put an opposing pressure on the side, it will move the other direction, hence DP, differential pressure. So when you look at the sensor designs, all we're basically doing is taking the old technology, the original pressure measurement of a U-tube manometer, and we're turning it to an electrical signal. So if you look at the representation that we have on the screen, this covers pretty much every manufacturer that you have in your plant, depending on the year or the evolution. These technologies, the first two I'm going to talk about are the ones that basically came out in the late 60s through the 70s into the 80s and are still current platforms. So the first one is a capacitance sensor. And if you look at that capacitance sensor, you have a red representation of the plate of the capacitor, and then you have 2 walls that deflects to, so essentially differential pressure. So if I put a pressure on one side, that plate will deflect over, it will give me an output. If I apply a pressure on the other yellow leg, it will deflect the opposing way and apply a pressure and give an electrical output. That is a very common technology. It's called a capacitance sensor. It is output in picofarads, and your atypical raw sensor, depending on the manufacturer, will range between 15 and 50 picofarads of output at the upper range limit. So for example, if you have a capsule range in your facility that will have a maximum rangeability of 250 inches of water, if I scale it all the way to 250, apply 250 inches, I will get that maximum picofarad output. It'll go to an A to D converter, and then you will get your output, whether it be a digital output like Profibus, Foundation Field Bus, or an analog output, which is your 4 to 20 milliamp part. The next sensor is piezo-resistive. This is basically a Wheatstone bridge. So the way this works is this sensor will sit there and deflect as pressure is applied, and what it essentially does is it throws an imbalance in the bridge, which gives you an output in ohms. So same principle, I apply on one side of it, it will give me a 250 ohm output. If I apply on the other side of it, I also get a 250 ohm output, which is my differential. Both designs are a metallic base. So if you look at the capacitance sensor, that red representation of the plate of the capacitor is metal. On the piezo-resistive, what they do is they take that circuit and they put it on a thin piece of metal or a foil, depending on the sensitivity. If I'm getting into draft range or if I'm getting into a higher range, that thickness will change. But at the end of the day, it's metal. And one of the inherent characteristics of these technologies, and it's just by the technology, is where you can get hysteresis effect. And hysteresis effect is essentially where you put a device in an environment that has a pressure. So for example, let's use a steam application to where I've got an orifice plate, and my orifice cut on is set for 100 inches of water column at my maximum span for my steam flow rate. But my steam pressure is 300 PSI. So as I apply that 300 PSI to both sides, because in the U-tube manometer, liquid seeks its own level. So if I'm in an equal format and there's no differential across it, the plate will see the same pressure. But every now and then over time, when it shifts, it can move a little bit. And that could be differential over time of the static pressure from the P1 to P2. And what happens is you don't see it until you typically go to an outage or you take the device offline. And if you isolate it, you will atypically see your zero elevated. So instead of sitting at 4 milliamps, what it will typically do is it could be at 4.2, 4.6 milliamps. And what occurs is it's just a natural hysteresis. So you try to zero that out when you do startup because you know that's going to happen. But if you don't, those are the results you'll see by using metal. The third one over to the right is a resonance silicon sensor. This is more of the next step going into a digital type sensor. And what they do with that is they embed what they call 2H bridges onto a piece of silica substrate. So instead of a metal, which we're talking about, the silica substrate is an elastomer. It's hysteresis free. So now it can sit there and it can flex up and down, but also return to its natural position. So think of your elastic on shorts or your jackets to where it's pretty much repeatable because it's elastic, but it always will stretch and return. So that is a technology. What they do with the sensors then is they drive it with a current. And what they do is they look at the shift in frequency output, and typically your output at your upper range limit on that technology is about 40,000 hertz. Then it goes into a D to A converter, and then of course you will get again your 4 to 20s or your digital outputs of your Foundation Field Bus or your Profibus. This is just a little bit more of a blown up diagram of what I'm talking about. And again, it's just a review of the variable capacitor, your fill fluid port. So your ports that feed that capacitor or feeds that Wheatstone bridge or feeds that resonating sensor, what it does is that's your silicon fill fluids that are between your actual diaphragms that make contact with your process. and then of course they will move the fluid. And those type of fills can vary. The most common is your silicone fill fluid for your daily units. You can go inerts and other types if needed, depending on the type of process, the compatibility with your chemicals that you have in case there is a possible rip in a diaphragm. But again, I would say probably 95% or more in your plant or silicone. So Endress+Hauser uses the piezo-resistive technology, but we also use capacitance, which I will talk about at the end of the presentation, but that's a different type of sensor for the chemical industry or any type of abrasive mediums. But for our daily transmitter, our DP transmitter, our gauge pressure transmitter, the sensor that we use is the piezo-resistive. But what Endress+Hauser has done with the technology is they have adapted the resonant silicon sensor technology to where you take the silica substrate, and with the silica substrate, what you will do is you will embed onto that the Wheatstone bridge. So what you're gaining is a very proven technology, just like the capacitance sensor, but what you're doing is you're giving it a better operating platform by going to the silica substrate. So you get that hysteresis repeatability, so it returns to its position all the time. That is a key player because part of our TPE, our total probable error, we actually calculate in the hysteresis effect, which some manufacturers don't do, but we can because we have changed that base to where you've historically gotten a memory. So the merging of, so I do one last thing. So basically merging the two, what you have is the best of both worlds. So the next thing is the capsule. So we talked about the electronics. The other is the robustness of the capsule. So I've gotten rid of the hysteresis. I'm still using a highly reliable platform for the core measurement, which is the piezo-resistive portion. But now let's talk about process effects. So what is your number one area where a transmitter can fail? It's typically the improper cycling of the three-way valve manifold. A three-way valve manifold or a five-way or two-way manifolds, they all have dual purposes, but let's focus on the three-way, and the five-way qualifies with it. It's just two additional valves. But when you deal with a three-way valve manifold, the purposes for it are two things, is isolation and calibration. So let me explain. On a three-way valve manifold, you can isolate it from your impulse lines that are coming to it, whether it be a flow application, whether it be a level application. But the whole idea behind that is while my process is running and I talk to my operators and they understand I'm working on that tag, I can actually take that unit offline without interrupting my process. Keep in mind, it is a signal going to the DCS, but at the same time, as long as the operators understand it, you can isolate it. The other is calibration. And the whole key behind the calibration with the three-way valve manifold is zeroing it. So spans, with the smart technologies of today, spans are pretty simple. You can go in with a handheld via heart. You can use your other platforms, AMS operating systems, any type of asset management system, since these are heart devices. But at the end of the day, what you do is you hook it up and you want to get a zero on the transmitter because that's actual live process. So when you isolate with the two valves, you must isolate and close them totally. And then that way, if I've got a little bit of differential pressure on both lines, it's captured in those two lines. And let's go back to our steam reference, 300-pound steam. So I've captured at those lines. But remember, that little transmitter is only measuring about 100 inches of water. So that's a lot. So what you want to do is open that equalizing valve, then it takes that whole 300 PS environment, even if there's a little delta between the two, and it equalizes it inside. So the transmitter is net neutral at zero static across either side. So the transmitter lives in a comfort zone because those sensors are not seeing that additional pressure. But what occurs in the field is when the manifold is improperly cycled, it could be a bad valve on the manifold that's not seating correctly. It could be somebody mistakenly only turning off the high side or possibly the low side. And then when they go down and they open up that equalizing manifold, what happens is you get a full pressure hit of the 300 PSI in our example against a 100-inch capsule, and you can potentially damage the transmitter, or the other is you are going to overflex and you're going to bend those metallic components we talked about in the sensor. So what I have for you on screen are some examples of what we've done in our DP capsule. It's not just a simple capsule with a piezo-resistive sensor. If you look on there, I've got the silica sensor chip. It's there standalone and it's going to do its job. But the key things I want you to focus on today is the pressure snubber and the absorption diaphragm, basically a check valve, the overpressure diaphragm. So the way it works is if I do have one of those significant events, these are two mechanisms that are key protectors to that sensor if that occurs, because the overpressure diaphragm will take the deflection and absorb that extra pressure, whether it's coming from the high side or the low side. And on top of that, that pressure snubber, for us that have worked with snubbers before, you can get a piston type snubber or a simple snubber that is a porous material that will just slow everything down immediately under a large overpressure effect. And that's what that little pressure snubber does. So what I'd like to do is give you a closer look at this. And if you take a look, this is the sensor cut away. So you have your overpressure diaphragm, and then you have your snubber right there. So that's what the sensor looks like. So the next is I want to talk about how we channel the fluid to the sensor. So now I have got a overpressure sensor. I've got a snubber in there to protect the high velocity, but also we channel the fluid around elbows to get it to the sensor, but it's not a direct hit, also under the overpressure event. So this is key because this will protect it in 3 different types of mechanisms we put in. We put a velocity check via how we plumb it. We do it via the overpressure diaphragm and the snubber. But here's the beauty of it. The update rate on this transmitter is that they say 90 millisecond transmitter. So it's extremely fast. So for safety systems, any of that, even though we've put all of these protective measures, the majority of them sit static most of their time. They're only going to be utilized if you have an event. But the nice thing is it gives you security, insurance, and protection to know that if that occurs, the device is protected. The other thing I just want to note on this slide quickly is we always get asked a question, do we have secondary containment? And that piezo-resistive sensor housing is a secondary containment on the device. So if you're in any kind of critical or chemical measurements, and that's a question that is standard in the Endress+Hauser offering. So the next thing is now let's talk about a third layer of protection we put on the transmitter. So the sensor capsule itself, it is out of a material that is a forged bar stock. Why? Most sensors in the market today are out of a cast, and they will cast them and then they will machine them and then they will weld on the diaphragms to do the measurement. We do it different. What we do is, since we use a forging, the first thing is forged metal, as most know, is very low in porosity. And one of the studies that's been done over the years is why transmitters drift and fail over long periods of time in non-severe service. The reason for that is because the fill fluid, that internal silicon fill fluid, it actually will absorb into the porous body. So by going to a forging, we're trying to reduce the failure and extend the lifetime of the device. So that's just one of the simple things. But one of the key things that we do is, if you look at this picture in the lower right, that and you'll see the 2 little holes that we have on there for filling, that does not have a diaphragm on it. And this is where we are a standout, totally unique manufacturer on the capsules. That capsule there is the bar stock machine. There is not a thin 3 mil diaphragm on that yet. So what we do is we take the two pieces, we put them together where we squish in the overpressure diaphragm, we do an electron beam weld, and then the next step that we do is we weld the 3 mil diaphragm to the capsule, which is your upper left-hand picture you're looking at. Notice one thing about it. There are no convolutions in it. It just looks like a little drum. What we do is then we take the individual capsule and we hydroform it with 6,670 PSI of water. So what we have done, and this is really important, what we have done is we have created a one-to-one relationship with the capsule to where we don't mass produce the diaphragms and get as close to the machining that we do behind it to get it to match. This is hydroform. Now, where this is very important is also on the overpressure, because if you take an overpressure event and you hit this, if you don't match the backside of it, you can get creases, you can get flattening. And for any that work with these diaphragms, this has a spring rate, no different than a diaphragm seal. You have a spring rate, so it's got to be sensitive. And anytime you change that, you manipulate it, everything changes. And the way you can tell is if you have an overpressure, you may be able to check that transmitter at 0 and span and get 4 and 20, but then do a 3-point or a 9-point check, and suddenly you may start seeing nonlinearity in the device. And a lot of times, if you take the flanges off, you will come into it, and right there, you will see flattening or a crease in there. So this is really important. These things are matched. The last thing is, most of us here in the Gulf Coast, we don't see freezing, but there is cryo services. And also we do get the crazy freezing storms like we had a couple of years ago. If liquid freezes on these, you can fully 100% compress this down. And when it thaws, it will return and it will give you the total performance, because this flattened out mirrors that backside when it had the hydroforming done. So the next step of protection on it is the gasketing. And on the gasketing, we obviously offer different materials depending on the process. But again, your workhorse transmitters out there, your most commonly used gasket, there's typically a requirement, and we use Teflon, PTFE. The beauty of this is we use instead of using virgin Teflon or a glass-filled Teflon, which Devin's going to show you here in a minute, that represents to where you have to go in and induce cold flowing. We use a spring-loaded Teflon-coated gasket. So it's like if you use Belleville springs, you know how you do a live loading. This is the same, except it's not two-piece construction. It's a single piece. And again, Devin will show you an image of it here in a minute. But what it is Teflon coated, but also you only require one torque spec. That's it. So let's say you have a transmitter in the plant and you got some process backing up into the impulse lines, you plugged it. It's a Saturday, you don't have a spare transmitter. You can get this thing, isolate it with your manifold, get it into the shop, tear the thing down, get it cleaned, check it. And if those gaskets are in good shape, you can reuse them, or if you have spares, just throw a new set of gaskets. But again, it's not it's only a single torque rate. So with that, I'm going to yield over to, there we go, to Devin, and Devin's going to show you a couple examples of the gasketings and what they, especially on the glass fields, what they look like pre and then what they look like after, and he'll explain what has to be involved to get them to properly seal for a long life in your plant without them turning into weepers.
All right, thanks, Pat. So what Pat is speaking of is this is your traditional PTFE gasket. You can see it's just before anything has been done to it to manipulate it. And this is what it becomes. So you can see the size difference. You can see the thickness. difference. And so what's done here is it is required a single torque, and then it must be exposed to a specific amount of heat, and then a retorque to get from this to this. And you can see that this PTFE ring will fit inside of the other. And where these go traditionally will be around your diaphragm here. And if you look inside of the flange, so you can see here, this is what mates up essentially. It will go into this little ring around. So we offer this PTFE coated spring loaded inside of this. Sorry, I don't have the correct size here, but additionally, what you'll see is you'll see these done here. So this is where your PTFE is gone. So again, comes from this, turns into this, so we can put it right in there. And what we have for a coplanar assembly based on Endress+Hauser is you can just put your gasket in there and plug it in with a single torque spec, as Pat mentioned earlier.
Yeah, thanks, Devin. And what he's showing you there is a lot of projects come in now to where they will integrate a coplanar manifold or a traditional type base to that technology. But the problem is then if it's integrally mounted to the manifold, you cannot field remove it, because if you use the manifold to isolate, then what occurs is you have to pull the unit off, but then you don't have the capabilities of doing the two-step torquing and the cold flow. What you're basically doing by inducing a temperature is typically about 180 degrees for about 4 hours. And what's required by that is you're inducing cold flow with that glass filled or that virgin Teflon to get that to move and to seal. Because otherwise, if you do an initial torque, and I've seen this in my career over years, to where somebody will think in good faith they've done it right, but then they will go into the plant, install it, and then they'll get a call out maybe 2-3 months down the road, and well, let's hope it's not nasty process, but it's weeping. It's weeping through the side, because what's happened is over the time in the process, that cold flowing has occurred and you've lost your torque. So yeah, very, very key. And the other issue too is just overall heat for any kind of horrible events that could possibly happen. Always having a metal surface, if you get fire or excessive heat or anything, metal's going to hold that torque. And that's why we went through this design, and why we decided to go to a Teflon coating. So you have the Teflon chemical resistance and also the sealing, because you're in transmitters like this, you're typically dealing in inches of water column. So it's a very, very small pressure. So you can't afford any kind of leak. You can't afford that at all. You have to have that pressure for one, criticality of the measurement, and most importantly, safety. Thanks, Devin. So the next thing I want to show you is we also do a capacitance sensor, but this is quite unique. This is highly used in chemical applications and gauge pressure now. This is not DP, this is gauge pressure. And what we do is we basically have 2 plates of a capacitor. So if you look at the ceramic cell, which is 99.9% ceramic, and over on the left, what you have is you have a spacer, and then your distance between your 2 plates of a capacitor that will give you the picofarad output like we talked about. And then the sensor itself, fully assembled. Note that there's no fill fluid in this. So these are excellent for vacuum applications, where if you're pulling a vacuum and you're afraid of boiling that internal fill fluid to excessive vacuum, or just straight chemical resistance, these things are dynamite. They come in a gauge pressure platform, stem mounted, and they work really, really well. So what I'd like to do is show you what these guys look like. So if you look, there is the pre-assembly of what the capsule looks like. And then with the ceramic on it, that's your ceramic surface. And then there's your circuitry that goes into the unit. The next slide I'm going to show is the process temperature rating for the ceramic. So we make two types. Since there's no fill fluid, really it's limiting your electronics. So it's like anything, you just need to isolate your electronics. So if you look at our standard, which is the capsule, or excuse me, the cell that I showed you, you can get the thing operating in comfortable ranges up to 130. You can push it up to 150. And as you can see, the charts are a little different on the high temperature and on the temp, the max versus the high temp versus the low. But at the end of the day, your operating ranges on that high temp, we can get it pretty hot. And again, these are a stem mount gauge pressure on the device. And then the last slide I wanted to show everybody is the Endress+Hauser electronics capability. So we've gone through how the capsule's built. We've gone through how we protect it from environmental process conditions, overpressures, hysteresis, all of that. So now it comes down to, well, how do I make it work when I get it out of the box? So we are still a little old school, and I'm really happy with it. We still offer push buttons on the display. So you can actually take an ENH out of the box, and let's go back to, as I like to do from my old days of service, the midnight scenario or the Saturday or Sunday scenario, and the handheld batteries are dead. You can't find the laptop, and you need to get this thing up and operational. The beauty of it is you do have the push button interface, and this unit, you can get it up and running. The other is, we also have external push buttons. That's an option. The push buttons on the front digital display, which by the way is standard on the device, those are always there. But if you do choose on projects to go to a blind transmitter, you can opt for the option or have both of the external push buttons, which are representative on the top of the housing of the transmitter. And then I talked about this earlier, but on the laptop, you can have your HART configurator. You can use any type of modem that's HART. We are HART 7 by default, and as you know, HART 7 is the most current HART, but it's also backwards compatible with HART 6 and HART 5. So the nice thing about that is it'll work with, if you've got an old 275, it'll communicate HART to it all the way up to, the modern handhelds. We have our SMT70 Field Expert, which takes HART signals in, Foundation Field Bus, Profibus, and the database for HART is all manufacturers. So when you get it, you can download it, or I should say upload it is the correct word, and you will have all libraries for all manufacturers. So it's not like the old days where you're locked out with a handheld for a specific manufacturer. Those days are gone. We need to, because we need to understand that what we're talking about today, you're averaging 6,000 to 8,000 of these typically in a refinery or a chemical plant. So you have to be flexible. And then the last thing I'll state that we didn't cover is Devin had shown the mounting. On our standard face-to-face, we are the 2.13-inch standard of everybody out in the field. So you can replace these, and with existing three-way valve manifolds by all manufacturers out there, we are not different than anybody else with that. So with that said, I think we'll go to questions. I ran over by about 4 minutes. I apologize, but I hope this was informative for everybody.
And we do have a few questions, Pat and Devin, so I will dive right into that. We do have a few minutes left for questions. First question, what communication protocols do you offer?
So as I had mentioned, we do HART, and again, we are HART 7. So you can go into any asset management system and you will not come up in generic mode. You will get full-blown menus all the way down to detailed setup and any of the advanced diagnostic features. We're also Foundation Field Bus. So if you have a Foundation Field Bus platform, we are with the most current revisions in Foundation Field Bus. And in Profibus, we are Profibus PA. So we hit all three of those protocols. And then again, the fourth one, which is just sort of neutral, you have the push buttons for configuration.
Okay, great. Next question. Does the snubber slow response or reduce sensitivity?
The answer is absolutely not. On our capsules, the way it is built and the way we channel it, we have very small porting. So your actual lines are small, so you do not lose that sensitivity. Our two capsules that are the most common are our 250-inch capsule and our 1200-inch capsule. Are 90 millisecond response time. So they're extremely fast considering all the moving parts and using a silicon fluid.
Okay, great. Will the Endress+Hauser transmitters interface with the AMS and other asset management tools and configurators?
The answer is yes. I've had personal experience with the Honeywell system and also with the AMS. We have many clients that choose to use the AMS as their platform, depending even on other manufacturers of distributive control systems. And yes, you have full configurability. We are members of the Heart Foundation. So as I had mentioned, we're Heart 7, and that keeps us current. But globally, we make sure with Profibus, with Foundation Fieldbus, and with Heart, we have a specific group within Endress+Hauser that is their job, is to stay current and make sure that we have all of the updates available to all manufacturers.
And next question, you mentioned the transmitter is the best of both worlds. Is there a drawback to the new technology?
No, not really, because the silica substrate really is the advancement in the sensor portion. The Wheatstone Bridge launched back in 1968 when the capacitance did. There were two manufacturers that led the market with it at the time. So that is very reliable, and that's why we didn't want to really change that. The resonant sensor technology is a good technology. It's still being proven out there, but what they learned from going to that platform again was the silica substrate base, to where you can now add the hysteresis into the calculation for the TPE. So when you're doing your total probable error, that is factored in, where historically it was not.
Okay. Do you offer electronic remote seal devices?
Yeah, so we offer it two different ways. I showed you the ceramic. We can do true electronic remote seals to where we will have two devices that will not. And so let me define that for those in the audience that don't know what the electronic remote seals are. Electronic remote seals were developed to try to help eliminate the drawbacks you get when you use a remote seal system, to where you will have historically long capillaries. And what you get with that is you get lag times, but the biggest thing is temperature effect, especially down here in the Gulf, to where you'll have temperatures in the summer that, depending on the heat deflection coming off the vessels, it could be 130, 140 degrees. And then out of nowhere, we get a wonderful Gulf Coast rainstorm. Temperatures will drop 30, 40 degrees. And suddenly your pressure transmitter turns into somewhat of a temperature transmitter. It'll move and drift. So the electronic remote seal was to eliminate that. So what we as manufacturers wanted to do was go to a self-contained electronic unit that could mate up to the fittings on the vessels, both the high side and the low side, and then run a coax cable down to a master. And then what it would do is it would take in the numbers off of those devices and become the output for the DP measurement. So we have done that. The nice thing with the Endress+Hauser product is the connectors for the high side and low side, they're universal. So all you have to do is take one off the shelf and address it. You don't have to keep a specific high side or a low side. So the answer is yes. The last portion is on our standard DP. Also, if you want to use a silicon filled sensor like what Devin showed you, we actually have a remote option too, to where you can remote the head, and the sensor itself is an environmental housing, so it meets all requirements. And then what you do is you run a coax. So if you're up on a catwalk or something and you want to bring that display down to eye level for maintenance or operators or safety, that is capable also.
Okay, great. And next question came in. This one's for Devin. Can you describe manifold options available as a package?
Absolutely. So Endress+Hauser has a package deal that can be put together with a Schneider manifold. Vector as well represents another manufacturer, Astava, that has great advantages throughout the industry that can be put together as a package. So as opportunities come about, we'd be happy to address those and see what would be best for your process and therefore.
Wonderful. Next question. Does Endress+Hauser make an electronic DP option?
Yeah, and that was the electronic DP is also known as the electronic remote seal, which I just talked about. And again, just to recap, these are independent sensors that mount to the 2 taps on the tank. And then instead of having a fill fluid in the capillary, we go to a coax connection to a master unit, which can be located at the bottom of the tank. You don't have to worry about elevation or suppression. That's the beauty of it. And then you get visibility, and also you have that first line defense against the thermal effect, either process or atypically just weather.
Okay, and we have time for one last question here. Do you have an offering for devices for safety systems?
Yes, the Endress+Hauser family, we are TUV SIL devices. So it's just an ordering code. So you get the certificate and you have the TUV label on it. So you can adapt it to any safety system out there. And so the answer is yes. And just please advise though, if it is for the safety system, because we'll ask you a few questions. Like, do you want red caps on it from a visual identifier in the plant? It's a real common request from customers. And then the other is just make sure you know it. So we do make sure it does have the TUV label and the certificate that shows up with it. So your safety officer has that on record.
Okay, great. Well, just a reminder, we do have our handouts available for the attendees to download. So if you have not done that and you wish to do that, please do that now. It's on the right hand of your controls. And we want to thank you for joining us today. We trust that you had a worthwhile experience and that you learned from our experts some valuable takeaways. Have a great rest of the day.